Hi everyone, my name is Huang Shusun. I'm reporting the title of this paper is VCM Allocator, a virtually contiguous memory allocator. This paper comes from IEEE Translations on Computers, December 2023. A virtual contiguous memory allocator, abbreviated as VCM allocator. The outline is 1. Introduction. 2. VCM allocator design. 3. VCM allocator implementation. 4. Evaluation and conclusions. This slide is introduction of this paper. 1. Static memory allocation occurs at a compiling time and involves assigning a fixed memory area known in advance. This type of allocation takes place at the stack memory level and lacks the ability to release or reassign memory during runtime. Dynamic memory allocation takes place in the heap's memory and accommodates size that are determined at runtime. 2. Indeed, reducing memory fragmentation, which attempts to reduce the dispersion of allocated rooms, is among the most important criteria for improving program behavior by reducing cache defects. 3. Due to this difficulty, only two contiguous memory allocators, CMA and GCMA, are proposed in the state-of-the-art. Both exploited in the kernel, used for the allocation of physically contiguous memory, which is all static and therefore does not require any resizing operation. 4. In this paper, the authors propose VCM allocator, a virtually contiguous custom memory allocator for the Microsoft Windows operating system, designed to allocate data structure confined in a virtually contiguous space that prioritizes memory. Fragmentation, while reducing memory and proportion overhead. 5. To solve the two singular challenges proposed by data resigning, the authors propose a strategy of virtually data movement by a remapping technique, avoiding memory copies that are considered time-consuming and energy-intensive. In Figure 1, the hierarchical of memory management in Windows shows the relation between VCM allocator, virtual page management, and the conventional memory allocators. VCM allocator leverages the AWE API to manipulate the mapping between virtual and physical memory. The authors offer a straightforward formula that allows users to apply the most appropriate strategy for their specific needs. This can include strategies such as perfect contiguous distributing containers based on size or data type, or any other relevant approach. The authors assume that all containers associated with the same hypercontainer are contiguous. Equation 1. While the hypercontainers are dispersed, containers residing in different hypercontainers are separated by the fact that hypercontainers are not always contiguous. Equation 2. Before allocate container, users must choose a hypercontainer or reserve a new one. This reservation is virtual and does not allocate any physical memory. This strategy is shown in algorithm 1. Algorithm 2 is the strategy of allocating a new container. Once a container is associated with a hypercontainer, enough physical memory will be inserted into the latter if needed. The authors propose based on strategy of remapping memory rooms, replacing the conventional strategy of data copying in equation 3. The deterministic approach results in fragmentation after reallocation. The authors define 3 reallocation strategies according to the nature of the data structure. Reallocation in container order, reallocation out of containers order, and reallocation of multiple containers. Algorithm 3. In reallocation in containers order, this strategy ensures the preservation of allocation order, thereby maintaining the integrity and linearity of data structure. In reallocation out of containers order, algorithm 4. Only the containers directly affected by the reallocation will be moved to the end of the hypercontainers if necessary. In reallocation of multiple containers, algorithm 4 can create a container for each dimension within the structure. When resigning the multidimensional array, all containers can be reallocated simultaneously using a single repainting operation instead of individually reallocated m times, where m corresponds to the product of dimensions in the multidimensional area. To release memory, the authors propose 3 functions. The first function allows freeing the memory of a container, which we consider as a reallocation operation to 0 bytes. The second function is applied at the level of hypercontainers and frees the memory occupied by the hypercontainer as well as its information system. See the algorithm 6. The rest function completely destroys the memory occupied by all hypercontainers. See algorithm 7 and the entire information system. The VCM allocated memory management system consists of 3 main contexts: container context, hypercontainer context, and the hypercontainer manager. The container context in Figure 2 holds information about the size and the location of an allocated memory block, including the user reference pointing to that memory block, its index in the hypercontainer, and its address. It also calculates other parameters such as the offset, mapping address, next available address, and the number of pages. The hypercontainer context, Figure 3, manages multiple container context instances within a hypercontainer and contains information about the hypercontainer size, container context, and PFN storage, and the number of allocated containers. For the implementation of VCM allocator context, 3 main data structures are created: VCM-CC, VCM-HCC, and VCM-HCM. The VCM-CC structure, Table 1, is used to represent a single container. It contains information such as the container's index, pointer size, and reference. The VCM-HCC structure, Table 2, is a higher level container structure that manages multiple VCM-CC structure. It keeps track of the number of containers and the page frame numbers allocated and provides storage for container points and reference. The VCM-HCM structure, Table 3, is used to manage multiple VCM HCC structures, providing storage for higher level container points and tracking the number of hypercontainers allocated. Table 1, Table 2, and Table 3 data structure are essential to the efficient operation of the VCM allocator. For the implementation of the VCM allocator APIs, see Table 4. We use the AWE APIs from Microsoft Windows. Requests for virtual address ranges are performed using the MS Windows API Virtual Allocator. The authors focus on the three criteria: speed, fragmentation, and the memory consumption. The authors propose two sets of evaluation: basic functions and real-world applications. The authors compare VCM allocator results to those of the default Windows 7 system allocator and to those of the most recent MIM allocator. The author obtained their results on a workstation equipped with Windows 7 and the MSVC++ compiler. Memory consumption statistics were obtained using MS Windows PSAPI, file cache, missing material were obtained using the Intel PCM library. And since the SPECCPU 2017 benchmark does not allow changes to the code, the authors extracted the code from selected application, modify it to support VCM allocator, and recompile it for all three allocators using the MSVC++ compiler. This series is intended for evaluating memory allocation, reallocation, and release operations in the context of regular data structures. There are two representations of 2D matrices. The first one, using multi-dimensional pointers or index arrays, see listing 1. And the second one, using affine array, a dimensional vector that emulates the behavior of two-dimensional matrices through a data access technique. See listing 2. And the first representation was chosen, as it is the only one that supports memory reciting operations. Listing 3. For a square matrix with dimensions m, the multidimensional point representation requires m plus 1 allocations. The authors observe that MIM allocation strengths, which distribute rooms based on their size, offers better fragmentation than M allocator. However, only VCM allocator produced a perfectly contiguous allocation without any fragmentation. FRG, AVG, average fragmentation, which can significantly improve the data structure's behavior. And in the case of VCM allocator, the second strength of all the multiple reallocations proposed by VCM allocators is choice, as shown in Table 6. On the other hand, the multiple reallocation strength proposed by VCM allocator C listing 4 show better performance compared to the MIM allocator strength. File display memory consumptions very close to M allocator during allocation operations. In general, memory disk allocation times are shorter than memory allocations, and the reallocation times as described in Table 7. Among the applications used to evaluate the behavior of data structure cache memories, we propose to cite the matrix multiplication. For data structure allocated by VCM allocator, we chose the optimal structure with a single hypercontainer containing points and the data, with all the pointers allocated first. See listing 5. VCM allocator, with its contiguous distribution, allows for two memory access models. Multi-dimensional pointer, also referred to as index array. See listing 6. Or affine array, a technique that emulates the behavior of 2D matrices using a 1D array. See listing 7. Figures 4, 5, 6, and 7 respectively represent the number of clock cycles energy consumptions, L2 cache missions, and L3 cache missions as a function of matrix size. The study found that VCM allocator outperformed M allocator and MIMA allocator in terms of cycle efficiency, as illustrated in Figure 4. VCM allocators superiority is attributed to the contiguous memory allocation it provides. The study also demonstrated that VCM allocator exhibits better cache mission behavior in Figure 6 and 7, and lower energy consumptions in Figure 5. As shown in Table 8, VCM allocator offers the best compromise, delivering better performance than MIM allocator without any excess memory consumptions. This paper presents VCM allocator, a custom memory allocator for Microsoft Windows that enables the creation of virtually contiguous data structure, reducing physical memory waste and the needed for data copying during reallocations. The authors' experience results validate the effectiveness of our proposed memory allocation, reallocation, and deallocation strategies. Thank you for your attention.